Hello, let's create a first-person... Hang on. Let's upgrade... No, we've done that. Let's create an extension to the Pixel Game Engine that will allow you to implement an entirely three-dimensional Raycast world complete with physics, collision and lighting. Now, I've already made 2 videos on the technology behind raycasted worlds like this. You might be familiar with them from games such as Wolfenstein 3D and Doom. And I'll explain my motivations for making this video towards the end of this video. However, here is a quick example of the Raycast world, and as you can see it has textured floors and walls, has skies, it has objects that are within the world, and it can even have indoor areas too. And in fact, as we'll see throughout this video, it can do a lot more than just this. Raycasted worlds like this are actually a 3-dimensional trick. The world is entirely 2-dimensional. And for every column on the screen, we cast a ray into the scene, see what it hits, and draws the appropriate response. And this is all technology I have covered in 2 previous videos. And so I don't intend on covering it again. And so this video is more of an applications video. How do we use the extension that I've developed? And I hope to convince you that it's really simple to use, and therefore you could add 3-dimensional Raycast world graphics to all of your games and applications. And what we should see by the end of this video is it's actually really easy to implement all sorts of cool, strange weirdness, such as this. And everything is handled for you by the extension. And so I have taken the code from the previous 2 videos and, well, completely rewritten it into a format which makes it very portable and easy to use. And I've packaged it up in a tool called a PixelGameEngine Extension, and they've been around since the Pixel Game Engine was launched, though I've not really publicised them very much. If you head on over to the OneLoneCoder GitHub and click on the OLC Pixel Game Engine repository, you'll see there are some folders in here, and one of them is extensions. And these are extensions that I've created and typically made a video about at some point, and the extension encapsulates functionality that will implement a specific thing, and presents that thing in a way that people that are familiar with the Pixel Game Engine will find quite intuitive. So for example here, the 3D graphics series ended up being encapsulated in the 3D PEGX. That's what we call Pixel Game Engine extensions in the community. And it includes all of the functions and code required to have 3D graphics, software rendered 3D graphics that is, in a Pixel Game Engine application. I actually went and used that in the Car Crime City video. But the really cool extensions lie in the contributions folder, and this is where the community have created things to enhance the Pixel Game Engine. For example, here is Gorbit99's Gamepad Extension, which allows you to have Xbox 360 and PlayStation 4 controller support in your Pixel Game Engine applications. And the extensions follow some simple rules. They must be entirely self-contained, and they should try and work cross-platform and require the most minimal amount of extra libraries, such as Matt Hayward's animated sprite PEGX. Typical usage is you just include the PEGX file, follow some basic instructions, and for example this particular extension will allow you to automatically animate sprite sheets. Some people go nuts and assume that the Pixel Game Engine just isn't good enough, such as Danderstein here, who created a Dear IM GUI, that's the immediate mode GUI extension for the Pixel Game Engine, so you can have graphical user interface overlays on top of your PGE apps. And just whilst I'm here, and I don't think I've mentioned it before, if you click on the Wiki tab of the PGE repo, there is actually a wiki telling you how to use the various features and a small tutorial that sort of gives you a step-by-step guide. There's still bits to fill in, as with all documentation, it takes time, but the crucial part is the most fundamental things are there, including useful utilities such as how to compile on different platforms. The very first iteration of the command line FPS introduced the concepts of raycasting and rendered it rather crudely in ASCII, but this seemed to have clicked with a lot of people. So much so that I then went to follow it on with a console game engine application, which introduced how we do texturing. But neither were perfect nor very transportable, and so that's what I've decided to do with this extension. It will allow you to construct a 3-dimensional Raycast world using any format you like. It doesn't care, and that's a crucial point. It will then allow you to texture that world in any format you like. Again, it doesn't care. You can populate this world with objects, and the objects can look like, well, whatever you like. It doesn't care. And finally, you can move objects around in this world with accurate collision responses. And all of that is handled for you by the extension. All you need to do is fill in the blanks. And so in this video we'll start off with a very simple implementation and then start adding more features to explore what its potential is. I've only been playing with it for a couple of days now, and I think there's actually a lot of cool tricks yet undiscovered. The Raycasting extension itself, at the time of this video, is version 1, and I would expect in the next couple of weeks and months that we'll see that version number increase. So if you're interested in using this, do keep an eye on the GitHub for updates. It's also not an especially large file, weighing in at just under 800 lines of code. But as I always try to do on the One Lone Coder channel, if you are interested in looking at how it works, I've tried to really comment absolutely everything with a sensible description of how it's doing what it's doing. But fundamentally there are two classes that we're interested in. The first is this object class, and both of these classes live in the OLC RCW namespace. The object class represents something that lives or inhabits the 3D world. What that something is, the Raycasting engine doesn't care, and you'll hear me saying this quite a lot. But an object must have a position and a velocity, and they can be translated into a speed and a heading as well. Objects also have a radius to say how wide they are in the 3D world. And there's a selection of Boolean flags that can be customized to change how that object interacts with the world, such as, is it actually visible? Does it need to be removed? What can it collide with? And what should we do when a collision occurs? The intention of this object is that it will be subtyped by the user as they see fit. For convenience, I've also added some basic controls to the object. You don't need to use them, of course, but if you do want to implement walking, strafing and turning, which is quite a common thing to do in a first-person shooter, then this will implement the maths for that. The second class here is the engine class, which is actually the PEGX itself. And how you use this class is up to you. So far I've been creating what's called an adapter class, and we'll see that as I create an example. But it's important to note that the engine class is abstract. That means it has some methods which don't have an implementation. You must provide something. But don't worry, that's not as daunting as it sounds. The engine makes a fundamental assumption that the world that it is rendering is represented as a 2D plane of cells, starting up here in the top left with 0, 0, and down here in the bottom right with a width and a height. Each cell in this world is a 1 by 1 unit tile, and this is a concept we've used many times on the channel. Even though the world is discrete like this, the objects that inhabit it exist in a floating point domain, so it's quite possible to have an object existing at this location, which for example would be 0, 1, 2, 2.5 across-ish by 1.5 down. So one of the first fundamental methods you must override is a particular location considered solid or not? Well, let's make a basic assumption that we represent our world as an array of booleans in this case, though it could be in any representation you want. If we chose a location here, then potentially this is a solid cell. The function would need to return true, as opposed to here, which is not within a cell, it would return false. And thus the user must override this isLocationSolid method, returning a result appropriate to how you've implemented the representation of your world. The engine will go away and calculate the mathematics behind the scenes to work out what the world should look like, but it doesn't know how to colour it. This colouring must be specified by the user by overriding this virtual function selectSceneryPixel, the arguments to which are the following. We provide it with the tile x and y, which is just the location of the tile we've just seen on the slides. It will also provide the user with which side of the tile it's interested in, and then it will also provide some additional floating point information for you to make some more, well, let's say interesting choices of colour, and we'll see that later too. So let's say that the engine has been instructed to place a camera at this location. The camera is also associated with a direction, so in this case it's looking at this angle. As with all Raycasters, a field of view is specified, and for each column in that field of view, a ray is cast into the scene. As the ray is cast, it might hit something. It'll know that because your isLocationSolid function has returned true. It will then query the derived class for, well, I've hit something, but what have I hit? What colour should I draw this? Well, in this example, we know the location of our tile, and it will also supply which side of the tile has been hit, the north, the east, the south, or the west. The engine will even know where on the surface of that particular tile have we hit, and it will return this information as the sample coordinates. At other points during the rendering process, the rays will want to sample things like the floor and the ceiling. And the same function is called for that too. The idea being is when that function is called, you will translate the coordinate information in the Raycast world, compare it to your world structures to work out what colour that pixel should be. And this sounds a lot more complicated than it really is, and we'll see during the demonstration it's actually very simple. There are some other abstract functions in here too, and we'll look at those a bit later for handling objects. The rest of the extension file is split into two main sections, one that updates the world and its inhabitants and performs collision detection. The second is the rendering process itself. And as I've mentioned, this has been discussed a few times in previous videos, although I have actually really optimized it considerably here, and I'll make a future video about one particular optimization which makes the ray casting very trivial indeed. For now, that's enough of the technicalities. Let's look at how we do it, and we'll start with a blank CPP file. Now of course it's a PixelGameEngine extension, so that means we do need the PixelGameEngine. And whenever I start a PixelGameEngine application, I just go to the header file and copy and paste the example project. And I'll remove all of the things I'm not that interested in. I'm going to set the resolution to be reasonably high, 640 by 480. Now the thing to remember with ray casting is it's entirely CPU bound, so if your CPU isn't quite strong enough, you might want to reduce this to 320 by 240 for example. Fundamentally, the RayCastWorld engine doesn't care, it will scale appropriately. To use the RayCastWorld extension, we simply define OLC PEGX RayCastWorld and include the extension header file. And now I'm going to define a class which will inherit from the RayCastWorld engine. I'll just call it example game. The implementation of this class is quite flexible and it depends on how you want to set things up, but right now I'm aiming for the most minimal example to get something up and running. I'll implement the constructor for this class and it'll take in the screen dimensions and the requested field of view. Because I'm inheriting from the engine class, I'm also calling the constructor of that class. Recall that the engine class is abstract. It has some methods that we must provide an implementation for. So I'm just going to grab those and pull them into our derived class, and then tidy them up. I'll now add a string to represent the map. And that's because I think strings are easy to draw in an editor such as the Visual Studio IDE, and for no other reason. However, you could represent your map however you want. And in the constructor of the example game class, I'm going to define that map. There we go. So smap equals, and this map happens to be 64 tiles wide by 32 tiles high. And if it's a full stop, it's an empty space, and if it's a hash, it's going to be a wall. I'll also populate a little vector with those dimensions. Now it's time to start filling in some of the blanks, and for this example right now I don't care about objects in the world, so I'm just going to leave those as is. I only really care about these two functions, is location solid and what is the colour of a pixel. Well, to test if a location is solid, I'm going to take the floating point coordinates it's providing and test them against firstly the boundaries of the world, because anything beyond the world I'm going to say is solid, so we're not rendering until infinity. And then I'm going to use those coordinates to give me the precise tile coordinate within the map, which is very simple. Here I'm checking against the boundary, and here I'm checking if the particular character at that location in our 2D string up there is a hash. If it is, return true. But if it isn't, it's empty space, return false. Let's now focus on how we make the world look like what we want it to look like. Very frequently, the engine will call select scenery pixel with the information outlined earlier. And it expects us to return an OLC pixel, which is just an RGB value, with which the engine can then render that to the screen in the appropriate 2D location. Well, right now I'm only going to render walls, sky, and ground. Principally, that's just 3 different colours. And I can decide which is which because the function provides me with this side argument. If the side happens to be the top of a cell, then I know it's going to be sky. I'll colour the sky cyan. If the side happens to be bottom, then, well, I know it's ground, so I'll colour that dark green. In this simple example, anything that's not sky or ground, well, that must be wall. And I'll colour my walls white. So right now we have derived a class from the engine called ExampleGame, but we've not yet tied it into the PixelGameEngine. To do this, I'm going to create a unique pointer to our derived class, pGame. And in my onUserCreate function, I'm going to initialize that pointer with an ExampleGame object, passing in our screen width, our screen height, and chosen field of view. It's approximately 1. In onUserUpdate, where we render the scene, the first thing I'll do is actually update the game engine. Then I'll tell it to render the world, but right now we haven't specified the camera location. The game engine itself provides a method called setCamera, which allows you to specify a position in the 2D plane and a heading, the direction the camera is looking in. However, I want to tie that camera to something in the game. I don't have to, but it does make things a little bit more convenient. And so even though in this example we're not going to draw objects in the world, I am going to add an object to the world which will be under player control, and therefore we can tie the camera to that. I'm not going to derive a class specifically for this, I'm just going to create an instance of object directly, called player, and give it a starting position, but set the visible flag to false, so the engine won't ever attempt to draw this object. Objects within the world, curiously, are stored in what is called a standard unordered map, which is a data structure we don't use very often on the channel. But I hope that over the next few weeks you'll see why I've made this decision, and I think it is the right decision too. All of the objects are in a publicly accessible map called Map Objects. And so I'm going to insert the player object we've just created with the key value 0. If that doesn't make any sense to you, for now just run with it, but an unordered map in C++ is effectively the same as a hash map in other languages. So I've specified a key, which is the value 0, and a value, which is the object player. Now I have an object in the world, I can assign some user input to control that object. For convenience, I'm going to add a floating point value fPlayerMoveSpeed, so we can change that and change the movement speed all in one place. Whilst I'm working with the user input of a specific object, I'm going to grab a convenience handle to that object by interrogating the map with key value 0 and storing it in a variable called player. This way I can interrogate the keys being held down, standard PixelGameEngine stuff, and call the appropriate function on the player object to implement that movement. I could also manually handle the player's physical position and heading. Turning right when the D key is held is exactly the same, except this time I'm turning in the opposite direction. Player movement we don't want to occur every frame, only when a key is held down. So most of the time, if a key is not held down, I'm going to set the player's velocity and speeds to 0. And this way, checking other keys, I can call the appropriate functions to walk forward, and strafe is effectively walking but at 90 degrees. By specifying the user input for a particular object, the engine's physics will then go and handle the movement of that object around the game world for us, including things like collision detection. Therefore, we can now take the position and heading of that object and attach the camera to it. So after the update function, after the physics have been updated for the world, I'll set the game's camera to be the same as our player's position and heading. So let's take a look. Oh, and we've got loads of errors, and I think this is due to a particular schoolboy error. In fact, yes, there's really useful output here from the Visual Studio compiler. Complete template hell. The reason is we're pushing in a player object into our map, when actually our map is expecting shared pointers to player objects. So let's just rectify that. And try again. Perfect. Let's take a look. So here we can see our world, it's rendering, we've got definitely a sky and we've got some ground, and we can see we've got walls. And if I press the A and D keys, I can rotate the world, and if I press the W and S keys, I can walk backwards and forwards in it. So the engine has successfully worked out where in the map should be sky, ground and wall. The only problem is it's quite difficult to actually see what's going on because we haven't got any texture or lighting to differentiate between different parts of the map. After all, why should it? We only ever supply 3 different solid colours to represent our world. Let's use this as a perfect example of an opportunity to show how we can abuse the select scenery pixel to implement what I am going to call ray shading, which is a crude attempt to make this sound far more impressive than it really is. Perhaps the first thing I want to do is shade things based on how far away they are from the player. So let's multiply our starting colour by a floating point value based upon the distance supplied to us by this function. The last argument is in fact the distance away from the camera, and it's a simple one-liner. We'll take the distance supplied by the function and we'll divide it by 32, so the furthest distance we can see away from us will be 32 tiles. I'm then clamping that so it's a value between 0 and 1, and then I'm flipping that so that ultimately we have 1 with pixels that are close to the camera and 0 with pixels that are further away. This means I can take the pixel that we have specified up here and I can multiply its individual R, G and B components by this value, and it will scale them according to how far away they are from the camera. Let's take a look. So now we can see walls in the distance are darker than those close to the screen, and it has added a little bit of relief to the scene. We can now start to identify that some objects are in front of others. As well as distance-based lighting, we could add some sort of universal directional lighting too. If we know that the side of the cell is the south or the east, perhaps we shade that darker to give some sort of shadowing effect. So I'll also add into our calculation here a modulation with the f-shadow variable. Let's take a look. Straight away we can see one wall here is much darker than the other, even though it's close to us. We've effectively added a directional lighting component to the scene. And there's a little cluster in the middle here. This has started to add some real depth to the scene now, and we can start to discriminate between walls. Well, almost. So as you can see, whilst we're crushed up against the walls, it's actually very difficult to interpret what's going on. That's because our walls lack texture. One way to add texture is of course to load a sprite and sample it, and we will do that in a minute, but let's look at a simpler way first so we understand the arguments being passed into us by the select scenery pixel function. By default a wall is all white, but I could use the additional information supplied by the function, for example these sample x and sample y parameters, which are normalized values across the surface of that cell. If I check that we are within the very boundaries of the cell, I'm going to return a black pixel instead. Let's take a look. So now we've not needed to load any textures or anything, but we are drawing detail onto the various surfaces within the world. And certainly a very stark detailing like this makes everything stand out. We go back into the labyrinth, we can see where the edges of walls begin and end, he says as he gets lost in his own labyrinth. So straight away what I'm hoping to demonstrate is that by some simple calculations we can really bring a sense of depth and realism into our Raycast world quite trivially. And I think that's a pretty neat level of flexibility, given that so far all we've done is implement the blanks of select scenery pixel and is location solid. We can of course introduce real world textures too. I'm going to create a variable type OLC renderable, which will help me load a particular graphic. In this case I'm going to load one called wall. And in the constructor of our example class I will load that renderable from disk. OLC renderables combine both the sprite and the decal. Now in our situation here we're not interested in the decal side of things at all. This is purely all software rendered. But now, for example, instead of specifying the colouring of a wall programmatically, I can look at the sprite component of the wall renderable, and since the dawn of time, sprites have had a function called sample. And I can pass directly in the sample x and sample y floating point values. These are just basically normalized texture coordinates at this point. Let's take a look. So now we've textured all of our walls properly, and we've combined that texturing with the distance shading and the directional shadowing. As this example is quite a simplistic Boolean map, I don't have any way of making a distinction between the north, south, east and west side of the walls. Right now a wall is a wall and that's all it will ever be. However, hopefully with this method you can see we could interrogate which side has been provided by the function and choose a texture appropriately from whatever level representation we have implemented. In the opening example, I used the editor that I created as part of my dungeon warping video to specify the tiles and the sides of the blocks, because that editor used some tricks of the Pixel game engine to allow us to render that in an interesting way. The point is, and I know I'm labouring it, that you can decide however you want what colour the pixel needs to be, because you are provided with all of the information you need to colour that pixel. Let's take a look at adding objects to our scene as well. So far, we've only added a player object, but let's add something that will move around the world on its own and respond to collisions, and we'll also use its position to change some of the lighting decisions that we make too. I'm going to add a star that will bounce around the world. So here I've created the base object, and I'm going to give it the generic ID 1. The game engine doesn't know what the objects are, only my derived engine does, so this generic ID can be used to link into your inner database of objects. I know if I get an object with a generic ID of 1, then it is a star, and I will treat it as such. I'll give it a starting location, and this object I do want to be visible. By default, objects have collision with scenery enabled. That's why our player object couldn't walk through the walls before. But in this instance, I want the star to inform me when it has collided with the scenery, so I can respond to it properly. Given that I want the star to obey the physics of the physics engine, I'm going to set its isActive flag to true. I'll set its size, and then add the star to the game world. In my derived class, I'm going to need another graphic to represent the star object. And I'll load that where I'm loading my other textures. Objects in the RayCastWorld engine are really defined by these three functions: how big they are in tile space, and in a very similar way to scenery pixels, we have to choose which object pixel we want the engine to display. For now, I'm going to leave these functions unchanged. My star will occupy an entire cell within the map. Recall a moment ago I set the generic ID to 1 for the star. Well, this is useful for helping me differentiate between objects in this function because the ID is given to me. So in this instance, I can check what the ID is, say, yep, that's related to my star, and then sample the star sprite at the particular coordinates. So quick recap, all we've done here is create another object, added it to the world, and provided the select object pixel function with a means to choose the correct pixel color for that object. So let's take a look. So I rotate, let's go and find the star. There it is, it exists within the world. I can change some of the physical properties of the star. So if I say that it can collide with objects, and I also say that my player can collide with objects, then when we run it, we can see the player can't walk through the star. And in fact, the player is currently pushing the star around the map. If I give the star a velocity, just by default, the star will now automatically move around the world given that velocity. There it goes, it's on its way. And it hit that wall and stopped. The star's not allowed to go through the scenery, and so it's statically resolved to this location. But let's make it so the star bounces off the walls. In the RayCastWorld extension header file, we'll see there's two optional functions which we can override. And the one we're interested in here is handle object versus scenery. I've added that function to our derived class, and it returns the object that's currently being interrogated, and it'll return similar information to the rays hitting the scenery, but telling us about how the object has hit the scenery. So again, knowing this information, we can decide on an appropriate collision response. I'm going to have a very simple response. In this case, if we hit the north or south side of a cell, I'm going to flip its y velocity. If we hit the east or west, I'm going to flip its x velocity. This will allow the star to bounce off the walls in a realistic manner. So off the star goes. Let's follow it into the world. It hit the wall and it bounced off. Let's go and follow it over here, hit that wall and bounced off. The star has a radius which we can't draw on the screen, but it's the edge of that radius hitting the wall which triggers the collision. And we can see it's bouncing around like a ball in an Arkanoid game, for example. And off it goes. In our scenery shading function, we could take into account the star's location to help us indicate some sort of point light source. I know in my map of objects the star was at value 1. I could use a constant identifier for that. I can work out the particular pixel the ray is interrogating right now, and then use the distance between the two to give me an indication of how close that particular scenery pixel is to our light source. I can then manipulate that light source into a value between 0 or 1, very similar to before based on distance. And instead of using directional lighting with this f-shadow variable, I'll change this to our starlight variable to give us a point source instead. Let's take a look. So now the world is very dark, but we can see where the star is illuminating the scenery. Interestingly, this reveals the sky is actually just a ceiling, so you might want to check for that beforehand, so you don't end up with this disk of light on the sky. In fact, let's throw in that code to show just how simple it is. We can check explicitly if the side provided is equal to the top. If it is, then I'm going to set my starlight to the minimum value of light that I want, which in this case is 0.2. Let's take a look. So now the star is moving around, but we're not shading the sky. The select object pixel function also has one additional argument, angle. First-person shooter games always look a little bit naff when the objects within the world are always facing the player. Ideally, you want objects with sprites from different rotational angles. Here I've created a little sprite that has an archer. I like archery. And so what I'm going to do is place this archer into the world and use that angle variable to select the appropriate sprite to draw. Now I've only got my archer from 4 different angles, the cardinal points. Ideally you want more. First I'll load the graphic for the archer, and then to the game I'll create an archer object and give it the generic ID 2, which in my system means 2 is an archer. I'll set its position directly to something in open space somewhere on my map, 40 by 12. And I'll set some other properties for how it can interact with the world. Finally, I'll add the archer to my map. Now I've got 2 sources of graphics in my world. I've got the star object, which has the generic identifier of 1, and I've got my archer object. So for now, I'll just draw my archer sprite. And this is going to look silly and broken. Let's definitely take a look. Let's head over to where the archer should be, 40 by 12, there it is. In fact, it's the whole sprite sheet of archers. Not what we wanted, so we need to scale the sample coordinate to be the specific archer sprite that we need. Hello Mr. Star bouncing around in the background. Choosing the sprite does have a little bit of mathematics involved. Here is the offset of the sprite into the sprite sheet in sprite sizes. I'm going to take that offset and combine it with the sample location, which is also in unit sprite size, and then multiply that by the width of the individual sprite tile. In my case, there's 64 by 64 pixels. I then normalize that entire sample point by dividing by the overall dimensions of the sprite. Now I can sample the archer sprite in the correct location. Let's take a look. Maybe I should have put the archer a little bit closer to the starting point. There he is, and he's facing away from us. Now the problem is, he's always going to be facing away from us. Doesn't matter what angle we look at him, it's no good. And this is why we need sprites at different rotational angles. And just whilst I'm here, I'm just going to quickly disable the starlight just to make the video a little bit more interesting, because it's getting a bit dark and gloomy. I can use the angle argument of this function to choose a particular offset, so I can then choose the correct sprite to show. And there aren't many ways around this other than just doing it manually. This will entirely depend on the layout and structure of your sprite sheet. The angle comes in radians, of course, And I have sprites facing 4 directions, so I'm splitting up my overall circle into 4 quarter circles and then choosing the sprite offset that I need. Now let's take a look. Well, at least it's a bit brighter now. Good. Let's find our archer. So he's facing away from us here, and as I rotate around him, we're now seeing his left-hand side. Now he's facing towards us. And now we're facing the right-hand side, and then we go back behind him, and we can see behind him. The more sprites that I have, the better this would look. Having just these 4 sprites still makes it look a bit strange, but hey, it's an old-school Raycast first-person shooter thing. It's okay. The engine's quite robust too. In fact, there's nothing stopping us having many archers. So I'll just modify where we're adding the 1 archer, and we'll add 1024 archers. We did some experiments last night on the Discord server and discovered that this was an amusing number. I'll start them all off at different positions. And I also want them to be facing in different directions too. This just adds a bit of variation, so I'm setting the heading value. So let's take a look with 1000 drawn objects and a star. There we go, we've got archers all over the place, and we can see our frame rate has taken a significant hit here. We mustn't forget that this is a purely software rendered thing. However, reducing the overall screen resolution will go a long way to helping you out in this regard. We can see the star, if we follow it, actually moves the archers out of the way. And that's because there's static resolution between the archer objects and the star objects. It's quite creepy. I also feel that the archers are a bit too large. We can use the getObjectWidth and getObjectHeight functions to change the size of the archer relative to a single tile. So they were occupying a whole tile, now they're occupying half a tile. So they will look quite small now, I think. That's a little better. Perhaps too small. We can use this function to also distort the shapes of the sprites. So let's say we wanted narrow archers, but really quite tall. We'll say that they're 2 tiles tall, and we'll turn them into giants. Yep, that looks terrible, and we seem to be at an inappropriate eye level with our combatants. If I reduce the number of archers to something a little bit more sensible, let's say 128 archers, we can also test the robustness of the physics engine by giving the archers a velocity. In this case, I'll set them all to 1-1, they'll all trek off in the same direction to begin with. There they go. And right now, because the collision handling doesn't make a differentiation between the stars and the archers, they bounce off the walls too. I'm happy with them bouncing off the walls, but let's adjust the heading to also match the direction of the velocity. This still looks very strange, but it's a little bit more realistic, I suppose. There really is no limit to how flexible you can be with this shading of the particular pixels. It gives you a scope for a lot of weird and wonderful tricks. And I hope that I've also demonstrated that the engine isn't in any way impeded by how you represent your world. It's also open for you to break the rules a little bit. So for example, we're taking the wall texture right now from a PNG file. But what if we took the wall texture from the previous frame? Well, the PixelGameEngine allows you to do crazy things like that. So if we take the original draw target, which was the screen, effectively the back buffer, we can sample that instead. Let's take a look. No doubt this will just be chaos. There we go. It looks like we've got mirrored walled surfaces now. They're not mirrors, of course, but it does look interesting nonetheless. I'm sure there are some creative types out there watching this which will already be thinking of ways to abuse this type of ray shading technology. I should definitely trademark that if it isn't already. And so there you have it. Totally bonkers, but very accessible, very portable, very simple to use. RayCastWorld engine complete with physics and collision detection. And I'm making that available in the GitHub straight away, so have some fun with it. There will be bugs and glitches and feature requests, no doubt, but please do get onto the Discord server or via the GitHub itself and show me what you've been doing. I said at the start of the video that I'll talk about my motivations for doing this at the end, and so that's what I'm going to do. My next few videos are going to be part of a series on networking using C++, and I'll be discussing ways that we can create flexible, robust and real-time client-server frameworks that should also be cross-platform too. On the One Lone Coder channel, I like to demonstrate technologies through the medium of computer games. Now, I know not everybody is a fan of that, but for me, games are fun, they're visually entertaining, which is good for videos, but they also impose this real-time constraint, and I believe programming under a real-time constraint makes you a better programmer. In order to make a compelling demonstration for that series, I thought it would be fun to implement a massively multiplayer online first-person shooting game, and I wanted to get the game aspect out of the way. I don't want to create another video on how we create a raycasting game. Yes, we're going to need to dip into that a little bit throughout the networking series, but what I really wanted was this video to show, here it is, this is the RayCastWorld engine, and we're just using it. We're not going to be going into the details of how it works. So I hope that's something to look forward to. I also hope that you've enjoyed this video. If you have, give me a big thumbs up. Have a think about subscribing, come and have a chat on the Discord server. All of the source code for this video will be on the GitHub, and I think the last two videos too. I've been a bit relaxed about putting the code up. Well, I'll see you next time. Take care of yourselves. Bye bye.